Hello guys, I'm Yash Khanolkar and today I'm going to demonstrate DLIC experiment 4, which is on the design of a practical differentiator circuit using op-amp OP07. Now in a practical differentiator circuit, as you might have guessed, the output voltage is the differentiation of the input voltage. So now we can go into the LTSpice software and we can see the schematic of a practical differentiator circuit where we have used the components R1, C1 and R2, C2. In the ideal differentiator we use R1, C1, but in the practical differentiator we have to add R2, C2 because if we don't add these components then the gain of the circuit becomes very large, which can lead to oscillations, which in turn can lead to noise. Now we can find the values of the resistors and capacitor by using the following calculations. So we have taken FA here as 1 kilohertz and FP here as 10 kilohertz. You can take this as any value you want, and we have assumed C1 as 8 nanofarad. So we can put them in this formula, and we can put the value of FA and C1 in this formula to get RF as 20 kilohertz. Similarly, we can put FB and C1 in this formula to get R1 as 2 kilohertz. In both the cases, we find that the time constant is same, so we just equate the equations and we get the value of CF as 0.98 nanofarad. And we can also find the R ohm here, so which is R3 in our case, as R1 parallel RF, so we get it as 1.818 kilo ohms, and we have taken this as 1.8 in our 1.8k in our circuit, and we have to supply the voltages here VCC and VEE as 15 volts, and we give an input sine wave with the DC offset as 0, the amplitude as 1 and the frequency as 100, and we give the transient time as 0.05. And now we can simulate the circuit. We can run this, you can check V in, you can check V out, and we can get the gain as negative. Then we increase the frequency of the wave and can put it as 1k. We then again simulate this and we zoom this, and then now we can find that the gain is almost unity. So now we can again increase the frequency to 10k, and we can again check this, check the waveform, and when you zoom this you can find that the gain is almost 5, and this is the highest gain you can get for an input sine wave. So you can even give other types of waves as input, like the square wave. So we will be giving the square wave as input. So for this we don't require the sine function, so we remove this. Then we go to advanced and we have to add a pulse where V initial will be -1, V on will be 1. We don't want any delay, we don't want T rise, we don't want T fall, we want T on to be 1m, and we want the T period to be 2m. Okay. And we also want the AC amplitude to be 1. Yes, so our input square wave is ready now. You can check the input. You can see the square wave is coming on the graph, and when you check the output when you zoom this, you can see the spikes which come when we have to change the state of the square wave. Now the square wave is not perfectly square, but this can happen when you have a little difference in the rise and fall time. In precision circuit this should be perfect. Now we can also do this for the input triangular wave, and for the input in triangular wave we just have to change the pulse value here. So just have to put this as 1m, and the fall time also as 1m, and this is 0. Okay, we simulate this, we run this, check the input, and you can see the triangular wave is appearing in the graph. And we check the output and we get an approximately square wave here. It's not perfectly square, but it's approx. And this is what you get when you give an input triangular wave. So another thing you can do is we can check the frequency response of the circuit. Now to check the frequency response of the circuit, we want to remove this pulse. So we remove this pulse. Okay, we don't want the transient response. Instead, we want the AC analysis. So we go to edit simulation command. We go to AC analysis. We give the type of sweep as decade, number of points as 1000. We give the start frequency as 1. We give the stop frequency as 1000 k. Now okay, and now circuit is ready to run, and we can run. We want the output, and output the frequency, and we can see the frequency response here. The line which is this line is the frequency response, while this line refers to the phase response. In the frequency response, we can see the at 1 kilohertz we are getting 0 dB, as we saw in the sine wave. At 10 kilohertz we are getting maximum frequency, the maximum gain, sorry, while at 100 hertz we are getting negative gain. We can also observe that the practical differentiator circuit acts as a high pass filter which attenuates low frequencies while giving a pass to the high frequencies. So this is all which I can show in this video, and it was a pleasure demonstrating this video, and thank you for seeing the video. Thank you.